Thank you, Deb. Thanks, Deb. Thanks, Deb.
I'll pretend like that's sincere.
Thanks, Deb.
Anytime. So I had several good questions earlier in office hours. I'll give you a few more minutes if anybody has any or there other questions from 7-1 or 7-2.
Can you do number 50 on 7-1 homework, please? Little funky.
50?
Yeah.
Oh yeah. Okay. Well, somebody else is asking about this. I gave him a little hint on what to do. I believe it says this, right?
Yeah. Equals 1 times 3
To the
times
n x.
squared.
I left out my little x there. And they want you to show that this equals 1 times 3 times 5 over 2 times 4 times 6.
2n minus
Yeah.
1.
These are all odds. That's how you write a general odd number. These are all evens times 5 or 2. So when you first read that, you're like, I don't know what you think I can do, book, right? So here's what you have to do. I love this problem. Of course I would. But we are going to see things like this a lot later this semester. We're going to work with them in different ways. When you first see it, you're like, what the hell? But here's the idea with this. This immediately screams to me, find the pattern. So what does that mean? What good is it? So this is for even powers. So if you let n equal 1, because n could be anything to make the power even. So n is 1, 2, 3, 4, so forth, right? And then you have to integrate this. This was, am I up in the right section? Yes. Okay.
Yeah.
So this would be sine squared x dx. Cool. And the reason I asked if I was in the right section is because this seems more like a next section problem. That's okay. How do I integrate this? So here's a big clue. You have that sheet. What's funny to me, again, is this is sort of a next section kind of problem. That's okay. And this was related to the half-angle formulas that you have to memorize. So for example, what's the sine of theta over 2? Does anyone?
Plus or minus root 1 minus cosine
Yes.
over 2?
Yes.
Dang.
Yes. Right? The rest of you guys are like, whatever, man. All right, so that's awesome. Okay. And again, that's on that green sheet that I put up on Canvas. Now, watch this. If I say, okay, if I do this and use this, what happens?
1 minus
Cosine 2 theta. The idea is whatever this is, this doubles it. And this is why it starts off as a half-angle formula, but then you can convert it, and let me even change variables. Square both sides, don't you get sine squared?
Aren't you working backwards now from?
Let me make this an x. Say again?
Aren't you working backwards now from?
Am I working backwards?
From 1 plus 1? Yeah, from sine squared plus cosine squared equals 1. Like, isn't that just?
No, definitely not. No,
not even
no.
close?
This is relating two trig functions that have different inputs, different angles inside. Those basic identities all have the same angles. Yes? All your Pythagorean theorem identities, they have the same angles. Is everybody with me so far?
Yeah.
So this is a half-angle formula. This is what they call the power reduction formula. And do you see how silly it is to pretend like they're two different formulas? Because we got this from this. And that happens a lot of times with trig identities. You can get other stuff from fundamental trig identities. So you don't have to memorize every single one of them. But they call this one power reduction because what's the trig function on this side? It's squared. And what about that side? First power. So it's power reduction. The worst thing about this is that's a stupid 2. If only it was the first power, it'd be easy as shit, right? So So I want to use something called power reduction.
So can we then?
Yes.
We can just plug in 1 minus cosine 2x over 2 for sine, we can just replace it.
And then you can integrate that. You have to be a little careful. It's going to be like, you can take a 1/2 out, make that a little easier to look at. All right. You guys sound with that? All right, let's do this. Keep going. The next thing I do is take a 1/2 out, so it makes it easier to just kind of work with what's really there. The 1 is going to be easy to integrate. This is going to, it's just got to be a little careful because there's a 2 inside, right? When you go to integrate it. Let's see what you guys get. You guys doing okay out there? All right.
This is number 50, right?
Yeah,
Yep.
sorry. I'm not doing okay. I don't like this uncertainty in the room at all. We'll figure it out.
So cosine 2x. No, So yeah, I mean, the 1 becomes x, and then it's minus, you're gonna have you have to change the word.
So the integral of 1, of course, is x. Take x. The integral of cosine something is basically sine something, right? So, but if you think it's sine 2x, you're wrong, because if you take the derivative,
Chain rule.
the
Yeah.
2 comes
Chain
out,
rule.
chain rule. So what has to be there?
1/2.
Yeah. And you want to evaluate that from, where do you go?
Yeah.
0 to 2.
What, wouldn't that be positives plus sine 2x, because
No,
that's not a negative cosine?
it totally is. Yep. What's the derivative of sine?
Cosine.
So the sign, the SIGN stays the same.
Oh,
Yes, I love
yeah.
it. So it's a whole changing gears thing, right?
Yeah, especially when you're dealing.
Sine and cosine really sucks for that. Because you got the derivative so beating your head, you gotta be careful about going backwards. But all you have to do is just take like a 5 seconds and go, okay, it makes sense, backwards, I see it. Nothing wrong with that. Write something down and then go, wait, does that work? And just see, does it work? And now I can just plug stuff in, right?
Mm-hmm.
So let's see, we get 1/2 pi over 2 minus sine of pi. Is that cool? And what's sine of pi?
0.
0. And when I plug a 0 in, I get 0 minus sine is 0, and sine of 0 is 0. So do you see, everybody understand? I plug a 0 in, I get nothing, right? Is that cool? So I plug a pi over 2 in, I get pi over 2 minus, what's gonna be 0? Plug a 0 in, I get nothing, so I don't even have to do it, because I can see it's gonna be nothing. Okay.
Pi over 4.
So you get pi over 4, and let's check it out. So look here. Isn't that the first piece of this?
Yep.
Times that?
Yeah.
So I'll bet you anything, and you gotta show this, if you make n2, make it a sine to the 4th, which is gonna be fun, you should end up, I'll bet you end up with 3 over 8 times pi over 2. You see, so you'll start to see the pattern. Really, you guys kind of see what I'm saying? We got the first thing. So for the nth thing, when n is when n is whatever, you go up to this. So if n is 1, how far am I going to go? What's this when n is 1?
1,
And then what's this when n is 1?
2.
So I go this far. When n is 2, how far am I going to go?
3 and 4.
3, 4. So I'm going to get this. When n is 3, I'm going to get this.
Mm-hmm.
You just got to show it. So I'd say if you do n is 1, like we did here, there's your gimme. Do n is 2, then n is 3. And then that's enough to show the pattern seems to hold. Now that, listen to me, it's one of the freakiest problems I've signed in there. Definitely. It's not a straightforward problem. You're not used to seeing things like this, correct? We're not used to seeing that. Jeff, what are you doing? But I thought this was a nice little baby step into seeing things like this. Yeah. It's going to kind of rule our life pretty soon.
Sums and series.
This is kind of a dumb question, but when you took the integral of cosine 2x, why is it 1/2 and not 2 in the front?
Oh, okay. So what's the derivative of
Oh.
sine 2x?
Uh-huh.
Yeah, yeah.
And then
So
do the
we're
integral.
thinking, if I thought that was the answer, a 2 would come out.
Mm-hmm.
There is no 2 there, so there must have been an over 2 that killed it.
Got it.
I could use U sub on that, but I desperately try to get my calc students to realize if the inside is linear, I do not have to use U sub. It's just the slope, it's just the coefficient that I gotta kill that would come out. Does that make, if you don't like all the depth in my math, just say cancel instead of kill. Okay. Is that better? I mean, and again, it's one of the harder problems, for certain. And it's not one that I thought, yeah, we could do this in a few minutes, no problem. No, this is a freaky problem. And the first freaky thing is, what the shit do I do with the damn thing? How do I analyze an integral that has got an n in it? You don't. You let n equal 1, 2, 3, and it's all about showing that pattern does show up. So when you make n equal 3, what should the answer be?
Pi over
What is that, 15?
What do you get on
3
top?
pi over.
3 pi over.
What do you get on top?
5 pi over
15
I love you
pi.
guys.
When you make it 3,
1 times 3 times 5.
15.
15
yeah.
pi
Pi. Oh my
over
God.
2 times 4 times 6 times 2, right?
48, 96.
I love it.
Yeah.
Okay, so that's what you should get if you make n 3.
Give me a
Make
break.
n 3. Okay, so try that out.
I've had physics in 2
I can see the excitement in your eyes. You're all like, oh yes.
I'm actually overcome short.
But at least now you know what to do. Yes?
Yeah.
Now you just gotta do it. I'm not saying that's gonna be easy, but at least you know what to do. Okay.
Excellent.
No, it's just a lot of legwork.
All right. All right, so let go of that problem. It's just one problem. It's not gonna be what the whole test looks like or anything. Okay?
Make sure I get that one.
Yeah.
I'm not gonna waste your time.
And by the way, you don't have to have like an entire chapter done before you turn it. Just when you're done with 7-1, give it to me. Give it to me as soon as you can, because then I'll have more time to look at it and get it back to you. That would be great. Now, some of you guys are doing the WebAssign thing. Great. Go for it. Right? And please, dear God, you could either bring in your laptop, or you can come into Mass Study Center. You can pull it up on the computer, and I can help you with whatever's on the website, on the internet. Yes.
Can we do both to build the extra practice?
Shit, yeah. Holy crap. I mean, hello. Yeah. I'm sorry. I'm not used to that kind of question. Yeah, extra practice, really smart idea. Right? If I wanted extra practice and I only wanted to do stuff out of the book, I would do some odd problems that I didn't assign, because then you have the answer, right? Okay. If you're like, I'm just going to do what you assign because that's all I get time, I understand. That should be enough practice, I think. Oh, does everybody got a mask? Mask. Do you know mask? Okay. They're always up here. Everybody else good? Yeah. Okay. All right, anything else? All right. All right, okay. So, let's talk about that thing we barely got into last time. We did an example, if I remember correctly. And everybody should have, let me go ahead and put this up here. Not you. Where did I put it? Did it run out? I think I did. Well, that's right. Everybody should have the trig, what's it say?
Trigonometric.
Trigonometric integration? Trig integrals, something like that?
Yeah.
Okay, I've given away all my handouts. So that handout I gave you is, kind of showcases the procedure to do, but let's talk about why those things make sense. So let me see, somebody have that handout? I want to kind of do it in the same order. So if we had a problem like, yeah. And actually, let's talk about a few things we need before we get into this. So it's basically all right here, all the kind of things you need, right? And then there's some more down here, but let's start with this by itself. So obviously, we know this, and then I've got the, then it's the other way around, who cares? And then I got the thing we just talked about earlier, the power reduction formula, and then there's the one for cosine squared, written a little bit differently, but it's still the same idea. By the way, see how cosine's still an asshole? Who did I steal it from? Me. Right, for the sine, it said, oh, you get a minus. And by the way, it's always me, even if it's sine, haha. Anyway, that's nothing mathematically rigorous about cosine being an asshole. I think you pick up on that. Just to me, it's kind of a funny thing to realize to help me remember certain things about the identities. Okay, maybe. You've already got them memorized some other way? Great. Keep it that way. So, the first example was, that's what I really want to try. Yeah, okay. So what if I had, so I desperately want you to see what we do, not as things to necessarily memorize, but just understand why what we do works. Do you see a function in here whose derivative is in here also?
Yes.
At least one, right? In fact, it goes two ways, doesn't it?
Yeah.
You could be either, what? What could u equal? What function do you see in here whose derivative is in there also, to some extent? Yeah, you use cosine, there's a sine in there. Or you assign, there's cosines in there, right? So it seems like u sub should work. I've got to be worried about one thing. I can only rewrite something in terms of the other trig function if I have an even number of those things.
So sine.
So I have an even number of sines, right? But I have an odd number of cosines. Okay. So if I let u, let's try this. If I let u equal cosine x, I don't want to let u equal cosine cubed. Holy shit. What would happen if I let u equal cosine cubed? It might work, but it gets a little weird. How do you take the derivative of cosine? If I let u equal cosine cubed, what would that derivative be?
3 cosine squared x
3 cosine squared x
times the derivative of cosine
Good.
x, which is negative sine x.
dx, right? And that's disgusting. And it might not be in there. It could be in there. You could actually try it sometimes, but let's not do that. In general, that's not going to really work too well. It might sometimes work. So what I'd rather do, if I try to let u equal cosine x, I want to show you how that leads to a problem. If u is cosine x, what's du? Negative sine x. And we all need to just not even care about coefficients. I can make them happen whenever I need to. So can I rewrite this so I see my du?
Yeah.
Yes. What do I do here to make du show up? I just take
Sine and sine cube.
one of those and slap it over there, right?
Yeah.
So I'm going to put a negative. I'm going to take one of these signs and put it over here. Is that cool? So I took one sign, took a negative, put it over there. Bam! Now I can see my du. Right? And then I got my cosine cube. So here's the problem. I need an even number of things to be able to rewrite it effectively. So if I let u equal cosine, du is this, but then what do I do with this? Right? I could take sine squared, right? What's the other one of these? Sine squared x equals 1 minus cosine squared. So I could rewrite sine squared in terms of this, but do you see how I have an extra sign? Damn it, right? So, no big deal. I just say, forget about that. All right, so let's set u equal sine, and the reason that should immediately make sense, if I make u sine, I know du is gonna be cosine. If I take one cosine off, do you see how there's a cosine squared that I can then write in terms of sine? There's an even number of cosines left. Do you see the idea? Okay, so if I try to let u equal sine, yeah, ideas. Neither one of you guys working? All right. Then du is listen. So and again, I know that some of your teachers, bless their heart, right? I'm from Georgia. That's their special way of saying something. They really. This is my opinion. I know it's all it is. It's my opinion. But we should never teach you to solve for dx. That's so crazy because you guys start doing these insane things and you think more can happen than it can. It's so much better, in my opinion. I know it's always my opinion. To construct what you need. I don't have to construct shit. I just have to pull one of these cosines off and I can find du. Okay, I like it. So see what this leads to. So if I pull one of these cosines aside, so everything's the same, I haven't changed anything, I will be able to find du. Now, here's the part that I hope makes sense. Now watch this. So what's this? According to my substitution. U to the fourth, right? What's this?
Du.
This is going to be du. What's this? You don't want du squared, trust me. Oh my God.
1 minus sine squared.
All right, good. So you can replace this with 1 minus sine squared. And of course, sine is u. There. That's why you need an even power left over on one of these pieces so that I can actually use one of the basic Pythagorean identities. Okay, I like it. It really is just u sub. It's just I got to be a little more creative according to what the powers are that I get. I like it. Don't worry, we're going to see how to use one of these. And now this, why is this so freaking beautiful?
Distribute and
Plug it
integrate.
all in.
Distribute. Integration's easy.
The fifth of
1/5 u to the 5th. What was u?
Sine x.
Let me write it better.
Sine to the fifth.
Yeah,
x.
1/5 u to the 5th. U was sine, so this would be 1/5 sine to the 5th. X minus
1/7.
1/7 sine to the 7th x.
Plus c.
Let's see, I like it. Nice. Poor little dude, you're dying. Oh, what are you? Are you good? You're probably not good. No, you're good. All right, let me stop for a minute. Sorry, I use the whole board, which sucks for the people in the back. If I do like this, you'll get seasick. I really want you to see how this is not that big of a step from just normal u sub. Not yet.
Yeah.
So we could have taught this back in u sub stuff. We could have totally done it. All right, so what happens? So let's try some more stuff out. So real quick, if you have your handout, do you see how at the top it's got sine to the m, cosine to the n. So if n is odd, like it is here, it says split off a factor of cosine, like we did. We split off a factor of cosine. Apply the relevant identity, this one, and then substitute u equals sine. Okay, I looked at the wrong place for a second. Oh, this is yours, okay. Are you in biology? You're in math, calculus? Anatomy. So yeah, that's next door. At least for tonight. It might come back over. There was a mix-up with the rooms.
Okay,
Okay.
Should we
I
make
love
a
it.
sign?
Anatomy is biology. That's right. Sorry?
Should we make a sign, put it on the building?
Oh, maybe.
It's
We'll see
too
if it
late for
happens
that.
anymore. Okay.
36.
All right. You guys okay? So again, if you wanted to, you could commit that crazy-ass handout to memory. That wasn't my purpose for creating it. I want that to be a quick little check as you're doing your homework. What makes sense to do here? Thinking ahead, what makes sense? You don't memorize stuff. Unless you want to, you can memorize stuff. But then you can only go so far in mathematics, because you get to a point where like, I can't memorize it anymore. And that's it, you're done. All right, okay. So let's try another one. Let's see. Everybody got this? Okay. right, what about if I have this situation? Right? I think we just did this, but did we just do this? Yeah, we did. Okay, so let's do one that's a little more interesting. Let's do this. I think this is in your homework, but it won't.
They're both even because the power of sine is 0? No?
Oh, I see what you mean. Sure,
Yeah.
sort of. Yeah. The problem here is, if you try to use U sub, there's no, U can only be cosine really. So I think it makes sense. And there is no sine in there to do anything for me. So what the shit? Yeah.
Could you break it off into two separate instances?
Yeah,
of
so I
minus-
know each one of these I can replace with that. So isn't this cosine squared, cosine squared? Yep.
Mhm.
So each cosine squared, let's write it like this, is 1/2 1 plus cosine 2x. 1/2 1 plus cosine 2x. Let me stop for a minute. Okay. What can I put out front?
1/2.
Be better than 1/4, good. You got 1/2 times 1/2, so we got 1/4. And now you just have to, what do you do with those? What do you think you do with those? Just, yeah, distribute, right? Or foil, whatever you like better. All right, let me stop for a minute. You guys, I can't do the same thing we did on the last problem because I don't have any signs to be my du. So it's not even an option here. But I do have this power reduction thing. Right? Yes?
I was to say, would it be dumb to, so after you do the split, would it be dumb to turn it into 1 minus sine squared?
All that would do, you would then have to use this, and it would eventually,
Oh.
you would put stuff together and it would eventually come back. Yeah,
Okay,
yeah, yeah.
gets you the same place.
But you're,
Okay.
this kind of question, there's nothing wrong with that.
Mhm.
Because, I mean, this doesn't look like a great thing, right? So you always have the motivation to try to make things better. And this is especially now, but it should have been in pre-calc, and I try to talk to my students directly in pre-calc about making math your own, right? So there are certain things I do that almost no other person would do with that, because it's my own thing. It just means something to me. I do it, so that no problem, right? You need to start doing that for yourself. And if you think you're like, oh, I think that works, show me. Show me, I'll let you know. And if it works and I like it, I'll steal it. I'll start doing it myself. Why not? Right? Okay, maybe. I don't know if you guys understand what I mean, but you just got to start playing with this stuff, seeing what would happen if you do that. And you're like, okay, that was didn't really go anywhere, but who knows, right? And by the way, just on a grander scale, math needs more fresh blood, right? That's not the best way to say it, but we need injections of fresh ideas every now and again. I like to think that I'm all fresh idea, but I've been doing this for a long time, so I'm a little set in some ways. We need somebody to come in and shake things up, right? So that's why I hope some of you guys keep going, get some more math in you, do some neat stuff. We need more thoughts about mathematics. Anyway, okay, I'll come back down. Okay. So now if you foil this out, does everybody see what's happening with that?
Yeah.
We're not used to using these at all. Right? Those are some like kind of forgotten stuff. The most you use it is like for the half angle stuff in about 10 problems. Am I wrong or right?
Yeah.
Okay, so that kind of sucks. That's a failing of our part. We should really use it more so when you get here, you're more aware of it. Now, how many 176 students end up in 280? Not a ton, so that might be part of why we don't. But it would be great for you guys to be more familiar with these. Instead of right now just going, yeah, that means everything now, right? So now I just have to foil. So you have 1 plus 2 of these, right? Plus cosine squared 2x. This and this are easy to integrate. What do you think you have to do with this guy?
Use another idea.
Holy shit.
Wait,
Sorry.
what?
Yes, for this guy, you're gonna have to replace it. Right? What's gonna, is everybody with me that this is easy? Yes. This is easy. maybe, yes, it's even easier because it already has a 2 that would be out there, so. And this, I have to do the same thing we did up here, except now, it's not gonna be 1/2, if I replace this, it's gonna be 1/2 times 1 plus cosine of what? It's already 2x.
4x.
4x.
Oh, what? This is weird.
Oh well, too bad. Now I know, part of you guys are like, God, I wish the problem had been over 3 steps ago. Get over that. I mean, and well, let's see. Risking some of you guys just leaving now. Later, you're gonna be like, oh man, I remember when it was just this long. I mean, at this point, haven't you guys done problems that went longer? I mean, we're almost done.
Yeah.
We're almost done. Already, right now, you should be like, okay, that was good. Didn't take up a whole page. I didn't have to turn. I love when somebody was asking me for help and they'd already turned the page over. You know, they turned the book over so they could write this way on the paper. Dude, I taped some freaking papers together for some of my homeworks. So trust me, I understand the the need for room. This is nothing, right?
Not exactly selling it right now.
Huh?
You're not exactly being.
Oh well. It's just, that's just the way things happen, right? So there are multi-step problems, and you know, not everybody majors in math because they don't have that interest in that. I understand that, but maybe some of you guys do. And almost everything we do in 280 has physical applications. People don't trust me on that. Do you guys know that complex numbers have physical applications? Any of you guys future engineers of some sort? Anybody? How many future engineers do I have out there possibly? How about electrical engineers? Anybody? Oh, electrical engineer? Yes? Ah, voltage waves, all about complex numbers. Without complex numbers, you couldn't do shit in electromagnetism. You're talking about wave guides and cool shit. And so like the real part is the electrical field and the imaginary part is the magnetic field, and they're both there, they both exist. Anyway, I'll stop, I'm sorry. So a lot of this stuff that we do in math that seems like some crazy dude who likes numbers, who's just bored and start doing shit on paper, they actually have applications in real life. I like it. Now me, I love the math that gets to the point where there is no applications at all. It's just playing with math, and I love that shit too, but I understand a lot of us just need, I want to see, what does this do for me? What does this do for us? What does this do for anybody? Right? Okay. Let's finish this up. Let's see. I'm going to write that up here. All right, and then I got this plus 1/2, 1 plus cosine 4x. Please tell me, does anyone not understand why there's a 4 there? It's okay if you don't. I mean,
Because you're doubling the angle.
yeah, so why is there a 2 here? Because it doubled that. So this is cosine, it's already 2x, so when I reduce the power, it doubles it again. That's all. Yes?
That was. Oh, but you can't do that with cosine to the third. It has to be cosine squared x.
Yeah, cosine to the third, you would split a cosine off and then attack the cosine
And
squared.
then do it. Okay.
Yeah.
So you're not. Is technically
Careful.
what you're doing
I see.
multiplying?
No, I see what you're saying.
You are.
So
just
for
doubling.
example, we had cosine to the 4th. I didn't take this and directly try to use that, did I?
No.
Because the rule says you need cosine squared.
Right.
You with me? But real quick, if I had cosine squared of 4ab, what would that be?
Cosine 8.
Cosine 8.
AB.
Well, it'd be 1 plus.
Right.
Cosine.
Cosine AB.
6 AB. No.
8
8ab, yeah. Over 2, right? That is the correct way to use that form. Are you guys with me? And unfortunately, that's another thing that you guys don't come in with a lot of practice, is seeing a form and knowing how to really use it. So for the real quick example, I know we still got to finish this, but I just want to show you. What's the sine of 2 theta? 2 sine cosine, 2 sine theta cosine. So I always see, once I teach that, I see somebody tell me this is this. I think the way I just said that tells you it isn't true, and hopefully nobody out there thinks this is true. Because what this says is, this angle has to be what this is twice of. So that this doesn't say, this is what that is. It's not what that form says. But it's really easy to misread what the form of something needs or means. Does that make sense? So that I understand. And that's going to happen. We're going to use the tables more than ever before. There's going to be a whole section about using the tables in the book. Did you know in the back of the book there's integral tables? Okay. If you didn't, you should really Whenever you get a new math book, you check out the back and the front, you see what the shit they give you, how many answers did they give you, you check all that out. Okay. So that's not true. What should it be? What's sine 4 theta? 2 sine 2 theta? Cosine 2 theta, exactly. Whatever this is, put half there and half there. Yeah. That's the correct usage. Yes?
I feel like I understand, but do the 1 plus cosine 4x one more time, because I feel like I'm not.
Oh, okay. So let's focus on that by itself. So where did it come from? It came from that cosine squared piece, right? And we know that cosine squared x, let me write it like this just so it's easy to look at, is this, right? We know that. So if I put a 2x here, that means I replace x with 2x, which means it would become 4x. Yeah, so it's sort of like function notation where you plug whatever's in there in, that kind of thing. Okay. So that's where this came from, is this is 2x, so this will now be 4x. Okay, stay with me. I love it. Okay, so I'll do this hard stuff here. Is everybody cool with that? Is that 2 that would come out is there, so I don't have to adjust anything?
Yeah.
I got everything I need, is that cool?
Yeah.
I'm not in the right place for my video though. Sorry, hold on. Okay, that'll work. I think that'll work, yeah. Let's see, now how am I gonna integrate this? It'll be 1/2.
Just spread out the 1/2. I would.
Yeah, I'm not gonna worry, because don't worry.
X over 2.
Yeah, this will be x. How do I integrate this?
Sine 4x over.
So, yeah, I like it. Sine 4x. It's not right, because if it differentiated, the 4 would come out. There is no 4, so this must have been over 4. I love it.
And then you can distribute the.
And it's not plus c, was it? No, I didn't make it definite. Okay. And then you can distribute, or whatever you want to do here. You can distribute the 1/4. You can take 1/2 out. You can take, anyway, let's see. It doesn't matter. Let's bring the 1/4 in. What is that going to be? 132? I think it is. 4, 2, and then another 4. Yeah. Okay. So what if the problem would have been sine to the 4th x? Then you would have. You would have done everything we did, except you would have just used this. Yeah. Right? Basically, would have looked very similar. Okay. All right. I don't know how you guys feel at the moment. Yes. Oh, you good? You're just scratching your head. Sorry. Okay. So let's go to the next level. So that's your sines and your cosines. So now we're going to talk about our secants and our tangents. No. Oh shit. All right. Can't always stick with the sines and cosines. Sorry. So help me remember a few things. What is the derivative of secant?
Secant theta tan theta.
Yeah, secant tangent. And what's the derivative of tangent's nice, right?
Secant
squared. Secant squared. So these problems are obviously going to be a little bit harder because sine and cosine, one's the derivative of the other one. Maybe sometimes it's a negative, who cares, right? So that's pretty nice and easy. This one, one derivative is the square of one, and the other one's the product of both of them together. Oh, God, okay. So you got to be a little bit more careful when you're approaching these problems because we're not as used to secant and tangent. We just don't use them as much as sine and cosine. So what if I had? Oh, let me see. Let's just try to figure out what to do with this. Make a problem, Jeff. I will. Yeah, let's do that. Sure. There's 2 ways to go with this, so I thought we'd start with this one. There's a very in-your-face way to do this.
You said, right?
Yeah. Both ways are u sub. So what's the first thing that came to mind for u sub?
U equals tangent.
U equals tangent. I love it. So we're going to do it both ways real quick. U equals tangent, so du is Secant squared, yeah, so I got everything I need for u sub to work, right? So I can rewrite this as, this is
UDU.
and this is du.
We're done.
What's up?
Pretty much. No.
And now you're all like, see Jeff,
You squared
that's
over
better,
2.
man. Why can't they just make them all like this? Is that so hard? For me, yes, too bad. I'll get used to this guy. So, and this is easy, blah, 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 blah.
You squared over 2.
So 1/2 u squared u was, don't do like that, Jeff. What was u? What do u be? Tangent?
And that's good enough, right?
Good enough, what do you mean?
Like that's
Is
the
it,
answer?
is it definite?
No.
No. Did we start with x variables?
No.
Yes, we did. We
We
started with
did,
x
yeah.
variables, and we ended with x
So that
variables.
is the answer.
That's the answer.
Okay. I thought you were gonna like start.
No, why would I? I did the integration, right?
Okay.
But I understand. A huge part of mathematics is just knowing when the hell to stop, because I hate it when students are like, okay, good, oh shit, why did you keep going? Oh shit, no. So I understand as a student, sometimes you're like, I'm not really sure when to stop, Jeff. So I understand, trust me. Is this I'm done?
I was gonna say, it's one of those things where it like seems almost too easy.
Okay,
You
this
can
one,
do it
this one was in your face, easy.
Yeah.
Can anyone see the other way to do this problem? That's not using this. Yeah, what if I let u equal secant? What's du then? Secant x tangent x. Now I like starting with this because you can pretty simply see that, can't you? Right now you can see it. You wouldn't normally think to look for that, but there will be situations where the powers are such that this won't work, this will. It depends on what the powers are and what's in there and what's available. So this problem, I'd really like to start with mine because it works both ways. Okay, does everybody see that? If I take one of these secants to be u, du is the other secant, other tangent, so everything's in there. So I can break this up into secant. I'm just going to do more steps than I normally would. This is going to be u, and this is du. Now we're going to get to a very interesting point here in a second. What's that integral? What's that integral? What's happening? What's that integral there?
U squared over 2.
Yeah, 1/2 u squared, and what was u?
Secant. So there's 2 answers?
Yes.
Those don't equal each other.
You sure?
Do they? They
I
do.
don't know.
They have to.
Yeah, they do. Are tangent squared and secant squared related?
Yeah.
Yes. So, let me stop for a second. Is everybody at least mostly cool with what just happened? Right? I know this is the way you all should have seen it first, right? Does everybody see that does work? Yeah? Okay. Do you see the problem we're having now? I tell you, these are equal to each other. And here's the real kicker. Are these C's necessarily the same? Oh, no. That's going to be huge.
Okay.
Can anyone tell me how tangent squared and secant squared are related?
Tan squared x plus 1 equals secant.
Yes. Tan squared plus 1 equals secant squared. And make the whole thing there. So I can replace this with tan squared plus 1. Right? And then this is 1/2 tangent squared x plus 1/2 plus c. And isn't this together a constant? Which is what this one is. So it didn't look like there's any way that could equal each other, but I really want you right now to start understanding that plus c, if you choose 2 different ways to do an integral, and your answer looks nothing like the book or somebody else, and you chose a different way to do it, the c is hiding a lot, right? You use some trig identities, you plug them in, you get some numbers, they all get sucked up into the c, and you're like, oh shit, they are the same thing. Maybe? Because that happens a lot. Where you do a problem, look at the back of the book, and you're like, holy shit, how? And you're fine, you're right. They just chose a different way to go. So they chose that way, and you chose that way. And you're like, ah. Okay, maybe. You guys doing okay? Yes?
Would you leave it as either way?
Yes, totally. What I'm trying to say is if you get this answer, and the book has this answer, you have to feel comfortable understanding and seeing that there's a relationship between this, and you can actually see they are the same.
That's interesting.
Isn't it?
Yeah.
Okay, I like it.
So if you took the, oh yeah, if you took the derivative, you just go straight back, huh?
Of course, yes, because whatever C is going to die either way. Yeah, maybe. All right, smart. Some of you guys are going to read better. I think that a couple of the first days were kind of like complete poker face. Okay. All right. What time we got? All right. So let's try another secant tangent problem and see what happens. And let's talk about some of the other stuff we need to know. So we got some basics. We got this. And of course you can just subtract 1 and solve for tan squared if you need it. Why do I have so many squares on that thing? I don't know. Ouch. And by the way, it should fit both conditions. So if you have this handout, you look at the bottom, M is on tangent, N is on secant. So here I made N even, M odd. Do you see how it works for both the first two procedures? And that's why there are two different ways to do it. Okay, I love it. So let's make them both even. Let's see what happens.
There's no example for what to do when they're both even.
See again?
There's no example to do when they're both even.
That's true. But all that matters, notice the only condition to use this
Is N even?
is N is even. So we're probably going to do that. But I kind of don't want you to even look at it right now. I kind of just want it to make sense. You're okay. I can either let U be secant, or I can let U be tangent, correct? If I try to let U equal secant, if U is secant, then I'm going to need, du is going to be secant tangent, correct? Okay, so let's see if this is going to get us somewhere. And obviously, the derivative being that is perfectly fine because I got a ton of secants and tangents to play with. Yeah, so I can certainly take a secant and tangent and make du easy. Now, I'm just telling you right now, this might not be the right thing. In fact, if you're following along your paper, you might know this is the right thing or wrong. Let's see which one it is. You don't have to. Stop. You're okay.
Oh, no.
I said if. So, if I let u equal secant, so that means I need secant tangent. So the very first thing I do is I make sure I can find du. So I would pull a secant, and I would pull a tangent. There's my du, right? And what does that leave behind? That leaves secant third, tangent fifth. Now if I let u equal secant, can I rewrite this using this? What's wrong with it that we can tell right away? It's got an odd power. It's got an extra tangent. Same idea with the sine cosine, because the Pythagorean identities all involve squares on the things that they relate, right? So the derivatives being a little bit weird between tangent and secant makes it a little harder to tell ahead of time what's going to happen. But right there I can see I've got an extra tangent. I'm not going to be able to go anywhere with it. Damn. So let's try the other way. So what if I let u be tangent? What would du be? Secant squared. That seems to jive because everything's even. My derivative is even, so I'm going to be left with an even number of things, and my identities need even number of things. So based on what I'm given, that does make more sense. So let's see. So if I make, where am I at? Secant. So I need to find secant squared. So I'm going to take two of these over here. That's my du. And then I got my tangent 6. And that's what u, so it's going to become u to the 6th. And I really want you to understand why I have to use the identities when I do. I don't have anything for this guy. But I can rewrite him in terms of what I let UB. Yes? So what can I use here? Tan squared plus 1. All right, so now everything fits, everything works. This is going to be u squared plus 1. Become a plus. That's going to be u6. And that's going to be du. And that's easy polynomial u business, yes? So if on a test you don't have it memorized and you forgot, did it really take long for me to notice the first way wasn't going to work? So I mean, part of this is accepting that part of the right way to do something is to pick the wrong way first. I mean, that's what part of this is. It's just like when you had to verify trig identities. Do you remember that?
Mm-hmm.
And you started with one side and you're like, I don't know, let me try the other side. Oh shit, you know. So, and then you're like, let me try this identity. Let me try this. So that's not right. So part of the process was just picking the wrong thing and noticing it was wrong. Maybe. So what I'm trying to get you to understand is, if you would have picked secant, and then you saw, well, that didn't work, don't freak out. Don't think that means bad things about you. So, all right, now you know that's not the right way. So now you know the right way. It's fantastic. Okay, maybe. Yes?
Is your goal always trying to make both powers even?
No. It depends on what each one has and what's left over. So especially with secant tangent, it's a little bit harder because one of the derivatives is secant tangent. So it's, I like the way you're thinking, but don't try to make it too general. It doesn't quite apply all the time. Okay. And this is simple, right? Is that cool? I don't even want to finish. Does that bother you?
No.
That's too easy. Come on. You guys, no? You guys want it? So u8 plus u6. So it'll be 1/9 tangent to the 9th power, right? Plus 1/7 tangent. 7th power plus c. Wow. Which is kind of anticlimactic, because I mean, that doesn't really mean much to us, right? I understand that, but it's just what it is. Funky. Yes?
Do we have to not, I know you don't like the word memorize, but like know these identities, be familiar with them, or will?
I'm fine with the word memorize.
Okay.
Just when people believe you have to memorize more than you really do, that's what troubles me. That's why I think some people have trouble with math, is because they're just trying to memorize so much. There's only so much you can memorize. So I can do a lot of math. I don't have a lot of math memorized. I can do a lot of math though, because, and I'm not, ooh, look at me. It's just because I know how to memorize what I need to memorize, and then I can build from there. So you do need to memorize something, right?
Yeah.
Like sine squared plus cosine squared equals 1. You got to memorize that. But then how do I build the other ones? Well, I divide by sine squared, I build another one. I divide by cosine squared, I build another one. I can build what I need from basic things I memorize. Okay. Maybe. Maybe. What's up? Sorry. Okay. So, let's do this. I think maybe one more of these. Yes. You guys doing all right out there? So much calculus. Okay. No, I don't want that yet. We're not ready for that. Oh, let's do. No, screw that. Doesn't matter. Blah 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 blah.
Give us a hard.
No, we see one.
How about? Let's do this. We did a problem like this a minute ago with sine and cosine. Let's try it with this stuff.
The impossible number.
Start taking rid of complex numbers.
Okay. So we did one sort of like this one earlier. It was like, I think it was cosine to the 4th or something. All right, so what do you have at your disposal? You've got tan squared plus 1 equals secant squared, right? Okay. That's pretty much it. I can't remember if I gave you, did I give you? No, that's pretty much all. Yeah, we're a little screwed with these, but can you, all right, just Anybody have any ideas
Split it
besides
up.
erase it and hope that I don't notice? You didn't do
Secant
it.
squared x, secant x.
Yeah, so, right, so it does seem to relate to secant squared. The very important thing is real. So why don't we just kind of break this up? Let's see what this does. So what can I do with that?
Tan squared x plus
All right, so, okay, so we can do, this is tan squared x plus 1.
Then u sub.
Well,
Not yet, no.
what happens if you try to do u sub?
Nothing comes out that equals the other thing.
Yeah,
No.
that's a problem, right?
Oh.
If you let u equal tangent, what's du?
Do you distribute?
2 tan.
If u is tangent,
Uh-huh.
du is,
2 tan tangent.
no, if u is tangent,
Oh. Secant squared x.
Yeah.
secant squared x. Oh, shit.
Sorry, I was thinking tan
No, you're okay,
squared.
you're okay. U cos tan squared would even be a little worse.
If you use secant, then you'd get tangent secant, which you don't have that. for tangent.
All right, so let's back up. So this might have been not the right thing to do here, yes?
Could we try integration by
Ooh, okay. All right, let me really make sure everybody's with us. It kind of made sense to break this up because this is related to an identity, right? And the secant and tangent are related by derivatives, so we're thinking about u sub, right? You think maybe we should try to use by parts. Why not? Let's try it. I'm gonna let you guys think about it for a second. Okay, maybe.
I don't know what I think.
What
You don't know
is
what
that
you're
equal what?
Couldn't you,
What could I do with this? Is there anything I could do with this?
couldn't you
No.
factor it?
a step?
You mean the opposite of that?
Distribute.
Distribute, I'm
I
sorry.
said that like.
I don't know if you realize this, but there's a lot of people in this room, so I can't necessarily always pick up what I say. Now, how does this help?
Now you have secant x tan x if you break it up.
This piece we could do,
Yeah.
right? Possibly.
Break it apart.
Well, I mean, this gets a little more interesting. You with me? But it seems like it might be doable.
Can we
This
secant minus 1?
could be trouble, yes? Okay, but it might be doable. All right. So, this seems to be another way to go to get to something more difficult. So if we try to do by parts, what was your idea for by parts, by the way?
Integrate secant squared
And
and then
differentiate this.
differentiate
Okay,
secant.
okay. So we could try it by parts here. Now, what I'm trying to let us do is play, right? I'm kind of letting you guys guide me. This might go somewhere. If we were thinking about by parts, it makes sense to let dv be secant squared. I think that's what you said, right?
Yeah.
Because then what's v? What's the integral of this? Tangent. So that means u is secant, and what's du?
Tangent secant, tangent x secant.
Yeah, secant tangent, yeah, or whatever. Okay, and then let's see what that is.
Well, you have the tangent for du and v.
Say again?
No, you have a tangent in common is what I'm saying.
Oh, I see, okay. So this becomes uv, secant tangent, minus the integral v du. What's it?
You end up where you started.
Exactly. Well, no, not where you started. What do you get? V du is secant x tangent squared x, right? Which is this. Yes? Okay, I like it. Okay. All right, so let me stop letting you play, sorry. Let's back up a bit. Okay. So again, we're just exploring stuff right now, right? We're just kind of seeing where this leads. So these don't seem to be getting us anywhere good. It looks like maybe I want to just try to work with that because it's showing up again.
Is that not the integral of the whole thing there? Secant x tan squared x
Yeah,
plus?
yeah, there's the dx, right?
Okay.
So that means that, yeah, these are bookends symbols.
So
Everything in
you
between is
sub
big
on
integral.
that part.
Say again?
You want to do u sub on that part down there that you've circled.
Maybe, yeah, exactly. We haven't tried to do anything with this yet.
So you would be secant.
All right, so let me pull this over there. we got, let's see. So if we look at this, let me do this. I'm going to go ahead and break this up into two separate integrals. Now this one is actually one that we can do, yes.
Could you rewrite that tangent squared x as secant squared x minus 1? Because then you would just have secants.
True, but then you wouldn't have the derivative of the secant, so u sub wouldn't get you anywhere. Yeah. Not a bad idea, but still not gonna work. This part is interesting. This part by itself is kind of interesting. I mean, you can think that maybe this will do something for you, right? But what do you think, all right, what do you think, how do you think you would integrate just that? Let's just look at this piece. How do you think you would integrate just this by itself? What would you try to use on this? Now, obviously, we can't integrate secant. We don't know what that is. That's the problem. U sub won't work, correct? All that's in there is secant.
Could you?
What's the only other method we really
By
know?
parts.
By parts.
Oh, could isn't it secant x is equivalent to 1 over cosine x? So couldn't you rewrite it
Sure.
as 1 over cosine?
You could. That's why I put that up there. Just, I'll put this over here in case this comes up later for us to do. All right, so what would you let u equal then?
Secant x, because we can't differentiate.
Secant x, exactly. You would never let dv be secant x, because that's the problem. I can't integrate secant. So I'm gonna let u equal secant. So du is
Tangent secant.
tangent secant. Sorry, I just always do this way. And then dv is gonna be so then v is x. So then what do you get here?
X secant x.
So you get uv, x secant x, minus integral of v,
X times secant x tan x dx.
Oh my
Right.
god, it's not even worse.
Yes, it gets a little worse. I love it, I love it. So, all right. There's enough playing around, Let me do this, all right. Let me come back to the beginning. Let's erase all this. In fact, let's do this. Let's just, okay. Let's start with this question by itself. Right, there must be some integral for secant, right? By parts seem to lead us to a strange place, for sure, right? What else can I tell you? If you do this, is there much of anything you can do with that? Not really. I love it. Because again, U sub doesn't work. By parts would be even worse because now you got some kind of quotient weird thing, right? I like it. Okay. All right. So, if you I'm trying to remember something. Oh yeah, that's right. Let's think. Let's do this. Okay. Let's go back to this for a second. All right. So remember we did I think we did this one by parts. E to the x. What was it? Cosine x or something? Remember that one? Okay. So there was the problem where it kind of came back to itself, and then we had to add it over and stuff like that. So let's do this with that in mind, where if I break this up again, right? So if I let u equal secant x, then du was secant x tangent x. And then dv is secant squared. So then v is tangent. Okay. So this is what we did a minute ago. Well, let's see if now that we're stopping to think about, well, what if we kind of had this come back to us? So let's see, secant tangent minus the integral of tangent. So this is where we ended up last time, right? Okay. So here's what we can do with this. Now remember, so this is the integral of secant cubed equals this. So this is the part that is strange. If I rewrite this, like we did before, I think at one point, or somebody suggested it, but we weren't sure where to go with it. How would I rewrite this? No, careful.
Secant squared x.
Yeah, I'm sorry, you said it right. 1 minus secant squared, okay.
No, I thought it was.
Tangent squared, oh yeah, secant
Yeah,
squared minus.
secant
thank you,
squared x
thank you.
minus 1.
Thinking too far down the road. Now, look what happens. Secant x, tangent x. But just to remind you guys, this is the integral of secant cubed. Secant x, tangent x. And then what do you get here? You get minus the integral of secant cubed plus the integral of secant.
We still don't know what secant.
Don't worry, we're gonna work on it. Now we have even more motivation to figure out what that is. Because now what can I do?
Add the integral of secant.
Yes. So they get 2 integral secant cubed x.
So tantalizing close.
Yes, and then a tantalizing integral of secant.
Wait.
What's up? Sorry.
Oh, you're just saying it equals out, okay.
So we saw this happen once before with the e to the theta, I think it was tangent theta, sine theta or something. I did that one on purpose because that was one of the times when the integral needed to kind of be brought back together. So now we're almost there if we could just figure out what this is. Right? You guys with me? All right. So I want to make sure you knew why I was trying to focus on what that was. Because now we basically have the answer. We just divide by 2 and we're done if we can figure out what this is. Now, let me do this. Can you look up, where is it? Here we go. So here's what's funkadelic. This guy here, let me see if you guys can get used to this. Can you look that up in the tables in the back of the book? Just to see, can you find that? Do you know where the tables are on the back? If you have your book, yeah. There we go.
Natural log of secant x plus tangent x. Absolute value of x.
Yeah, I don't personally get that without the book.
Plus
I know. So this is one that we're gonna learn how to do later. We don't quite have the right stuff yet. So even in the book, when you see this, it says to use the tables to figure this out. So I was trying to figure out in my head if there's a way to do this earlier, now with what we know, and we don't have enough to do this yet. So I was trying to figure out, as I was up here, I'm like, is there a way to do this now? No. And sure enough, the book has it as a problem. It says, look this up in the table and you get this.
Oh,
Very
very helpful.
helpful.
I know.
Punch.
There is one little trick you can do to do it, but it's just kind of weird. Anyway. In fact, really quick. I think I was kind of deciding whether or not to show you this, but I think I'll show you this anyway. Because this is one of those things you just have to. Do you guys remember when you did proved I think it was the product rule for derivatives?
Mm-hmm.
And you had to, if depending on your teacher, you had to add and subtract the same thing in the limit. I don't know if you guys remember. That might be too specific of a thing to remember. You remember that? And it was like, well, how do you know to do that? So watch this. If you multiply this, is it plus yet?
Just keep going.
I know. I'm going to stop now. But if you do that from out of nowhere, correct?
So if I multiply by 1,
Huh? Say again?
isn't that just 1?
That's why I'm allowed to do that. Understood?
Yeah.
I can multiply top and bottom of anything by the same thing, right? as long as the bottom isn't 0, right? So this kind of like doesn't allow x to be anything that makes this 0. But if I do this, believe it or not, I can then, I'm not going to, just wanted to show you, there's a weird little trick you could do. If you want to try the rest of that, you can. I'm not going to focus too much on that. But I was up here trying to think of myself, is there a way to do it without that little trick? And I couldn't think of a way, so. But that's a little trick you could do. It's sort of related to stuff we've seen in the past, where we add and subtract the same thing from out of nowhere.
Yeah.
Okay.
Just a fancy form of 1.
Yeah. So, in your homework, you're not going to see this guy. But you will see powers of secant and tangent. So somebody help me out. What's it say? The very first secant tangent problem we did fell into both categories on your handout. So it was n was even and m was odd, right?
Yeah.
So let's do a normal one for a second. Let's see. What if we make tangent, then what if we make them both odd? Okay, let's try this guy. So they're both odd, and I kind of like, I think, Abiel, it was you earlier who said trying to make them both even. It's not quite that, but very often it does sort of lead that way because a lot of our identities have squares in them, right? So these are both odd. If I try to do u as tangent,
No, bad idea.
right? Can you already see it's not gonna, because how many secants would I shuck off?
Only 2.
I would need 2, right? The du would be secant squared. So I'd pull 2 over and then I'd be left with an odd. Yeah, okay, so you guys see the problem? I really want you to see the problem. Our basic identities involve squares. So I want to be left over with a piece that's got an even power, so then my basic Pythagorean identities can help me, right? So I'm probably going to use secant. So then du would be secant tangent. All right, take a minute and try to work with that a little bit. I'm going to let you guys do some work.
Okay, Joe.
Do you get this page today or was another day?
It was last time.
Oh, okay.
And I've given them all out, so. If somebody will remind me, I will try to put all the handouts up in Canvas in case you lose it or you weren't here or something. I just need to remember. I don't really use, I don't
When
like
do you want us
Canvas
to
too much.
remind you?
If anybody would just email me and say, hey, don't forget to put, I won't be able to read it in your voice or whatever you're saying.
This one's bad. Okay.
Just remind me. Most of you guys know I do this. Yes?
Can you break things off twice? Like take one section off and then take another section off?
Mm-hmm.
Is that what you have to do here?
And then
Possibly.
what is it? 1 minus. Hello?
Interesting.
Just to make sure everybody's on the right track. When you identify this, the very first thing you should do is do whatever you need to have this show up. Because then you know whatever's left over you need to play with. You want to make sure you get your du created. And that's another reason why I hate solving for dx, because then you're not really thinking about it the right way. So I need to pull a tangent and a secant. Over.
Then we replace tangent squared x.
With secant squared x minus 1.
Yeah, because now u is secant, so this guy's good. He's the problem, and I think now you understand whatever's left of the thing that's not u needs to be written in a form that has the u piece in it, obviously.
Yeah.
Because then I can actually plug some u's in.
And you can rewrite that as secant squared x minus 1.
Yeah, so this guy,
Which will just become u squared minus 1.
so I'm gonna write all this crap out.
Okay, yeah.
Alright. It's fine to write stuff with some u, some x if it's in the middle of your work. I'm just not gonna do it. So then now plugging stuff in, this becomes
U squared minus one.
U squared minus 1.
Times u to the fourth.
U to the 4th, and of course this is just,
Du.
and this is what you really want to see.
Oh, I did it right. Oh, wait, no.
Just a nice polynomial in U.
Oh, it's secant squared x minus 1, not
Yes.
1 minus secant squared.
Exactly.
I was thinking.
This is tan squared plus 1 equals secant squared. And secant squared
Right.
minus 1 equals tan squared. And if I were you, I would just write that real quick on the top of my paper, like if I was about to take a quiz or a test or something, right? I've had teachers that don't allow memory dumps. Have you ever had a teacher, they specifically did not allow us to write a bunch of things.
That's not fair.
Yes.
That's
I don't
kinda-
care. Yeah, but,
So,
it's not like
Wait, so
We
what
just-
would we write down?
sorry,
At the top?
just tangent squared x plus 1 equals secant squared.
distribute your,
Right, just write that down, so then you can just look at it every time you need it. Sorry? No, so, I mean, this is obviously very important to know. So I'm just saying, why not write that down at the top of your paper? Not even because you don't remember it, but just so you can kind of look at it, right? Just to
Because
keep
I don't
yourself straight. True. That's how I always used to memorize something, is I'd write it, and then it'd be in my head. Yeah, I would rewrite my notes once, and then they were sort of in my head, and I would never have to look at them again.
oh, so yeah, I would just like say it over my head. If I got it wrong, I'd like staple
I
it.
think
Holy shit.
What?
Okay, well, all right.
Just
We're not gonna, I'm not gonna
At
recommend
least right now.
stapling yourself.
Oh my
I
god.
highly recommend
That got dark.
you don't
Yeah,
do
I
that.
feel like it's the same.
Dude, that's amazing.
That's why the stapler's so red.
Yeah.
Do it there.
That's the last thing I expected to hear.
Like after some practice, I'll be like, okay.
This is cool, guys. So most of these are gonna get to a point like this polynomial in U, and then it's basically the same thing we did before. Is that cool?
Yeah.
Okay, not too bad, not too shabby. Okay, I like it.
Too shabby.
I like it. So again, this situation where you just gotta get in there, try some stuff. We got plenty of time, so I'm gonna, oh shit, you guys love it. We're gonna sneak a little bit in the next section.
No.
Oh shit. Okay. Oh shit.
Like 25
This one is painful. I know for real. 7.3.
7-3?
Yeah.
I haven't even gotten there yet.
Okay.
It's not pretty. 7.3?
So I kind of, listen, guys, we're not gonna, we'll stay a little bit after 7, we're not gonna stay forever, and we're not gonna get all the way through this. I'm kinda like introducing something at the end of a class, and then we pick up with it the next time, so your brain's had kind of some time to at least mull it over in the back of your brain,
It's a marinade.
is my hope.
What's the name of this chapter?
7.3, trig setup,
Trig setup?
trig sub,
Oh my
trig
God.
substitution,
Sub?
trig substitution, just like we have u sub, we have trig sub. Now listen, guys. I know I'm not your standard case, but I remember learning this and going, holy shit, that's amazing. It's just such it's a type of substitution that once you see it a few times, you're like, okay, that makes sense, but I would have never thought I would be allowed to do that, right? You know what I'm talking about, okay. Some of you guys have gotten ahead a little bit. I love it. Okay. So here's the idea. This is what I'd love to start with, something that doesn't seem like it's related to calculus at all. You guys want to take a break from calculus for a minute?
Yes.
Okay, so, given this, I don't know why I'm using an 8 necessarily, but. Yep. That's a 9. 90. Try this. What is f of 3 secant theta?
This is fabulous.
Right? No, listen. Isn't this, all right, I could have asked you f of w, I could have asked you f of 1 to be nice, right? But I didn't. I asked you this, and who gives a shit? The first step is the same. We know how functions work, correct? You guys with me? And you're all like, when you said no calc, I didn't know you'd be doing this, but, oh well, too bad, it's not calculus. It's barely even trig, to be honest. It's just whatever. If I put f of Jeff, wouldn't it just be great? Jeff squared minus 9? j squared, e squared, f squared, s squared, f to the fourth. All right. So what do you get then? If you put that in, you get 9 secant squared theta minus 9. Yep. Can you do anything with that to simplify?
What's the trig identity?
Take that out.
Can you take a 9 out?
Oh, okay.
In fact, it'd be square root of 9 with me.
3, that's great.
Yeah.
Is that cool? Hold on. So, some of you guys, no matter what I put up here, you're looking like this. No matter what I do. All right.
So that's a 3.
Listen. This is totally a problem. You could have been given in 110 even. You don't have to know what this is. It doesn't matter what the shit I put here. You just put it in, right? But now we're going to use some of our knowledge. We know what the hell this is. So what is secant squared theta minus 1?
Tangent squared.
Tangent squared. What's square root of 9?
3.
So you get the square root of tangent squared. And if I assume that I am such that all my trigs are positive, what's this?
3 tan theta.
3 tan theta.
That's so nice. That's cute.
Okay, maybe.
Good times.
Okay, now. I love it. Some of you guys are going, okay, Jeff. What does that have to do with, like the class we're in? Can you, bring it back? Okay. So, if I had, so has everybody got this here?
Mm-hmm.
Okay. Can you imagine, what if I would have wanted you, I really want you to understand, why did I make it 3 secant theta? What was this that told me I had to use secant? What was it about this form that told me that secant would work?
X squared minus the constant.
Yeah, because because it's secant squared minus 1, so it's the function squared minus 1 that equals something else. So that form told me secant would work. So what do you think if I wanted to use sine? If I wanted to use sine and I wanted it to be nice, like how would I need to change
1
this?
minus sine squared equals cosine.
I love it. So watch this. All right, so everybody's got this?
I don't like where this is going.
No, don't worry. But you're the one that just said where it was going.
I know where it's going, but I don't like it.
So watch this. Maybe this X just, I don't know why I made it A.
Okay.
So what if I had this instead?
Oh no. Oh wait, it's a perfect. No, it doesn't have to be perfect square.
Don't, you can't. Give me a break. Don't do that.
Okay.
Why can't you do that? I've always been.
Please, dear God. Okay, a little side, sorry. Um,
I'm sorry.
No. I'm sorry, Carmen. It's something for teachers. All right.
I've
Can you do
never
the square root of?
understood
Oh no, that's not what I was saying. I was saying that does a constant need to be able to be rooted like perfectly, or?
No, it doesn't.
No? Okay.
It doesn't.
Because the last one was a 9.
But what are you talking about then?
Like, why can't you take the square root of 16 minus x squared? It's probably a stupid.
And you think it would be what? 4 minus X?
Yeah.
Okay.
I've never.
No, it doesn't need to be.
That's not what I was saying.
I'm just making it for now.
Well, if you were to do that.
Well, you can't have a negative.
Now
That's
listen.
true, because we don't know what x is.
Can you do the square root of 7?
No.
Nicely, right? There's an answer about if I said, what's the square root of 7? You can approximate. You can go, it's 2 point something, dude. Okay. Even though, isn't 16 minus 9 7?
Yeah. It's because we don't know what.
So
x
if you thought that this was this, does 4 minus 3 equal the square equal
No.
square root of 7?
No. Okay.
So listen. Remember, this is another reason why I wish we never invented radical notation. It's one of the dumbest things we've ever done in history. What does a square root actually mean? It means that thing to the 1/2. I know that I can't distribute powers across addition and subtraction. We know that. A plus b squared is not a squared plus b squared. Because squares aren't based on addition. So they're not going to play well together. Whereas if I had ab squared, I could pull that in all day. Because now what's the operation on the inside? Freaking multiplication, which is what exponents are based on. That's why they play well together. So we forget radicals are powers. I cannot distribute a power across subtraction or addition because those operations don't play together. All right, sorry.
No,
But
that's
I'm
fine.
sure you're not, I get it all the time. And then people are like, you said that problem's gonna be hard, and I did it quick. And I'm like, you got the wrong answer quick as shit. You did this. So I understand the optimism and that it kind of visually makes quick sense. But It's because the radical, if it was just the power, I think we'd make that mistake less. Because we know I can't bring powers across addition and subtraction. Okay. So this one, what do you guys think I would put in here to make things work? We sort of gave it away a minute ago. It's got to be signed, but what's the number got to be on it?
4.
4, because square doesn't make it significant. Okay, so this will be
16 minus
4
16 sine squared.
and of course, square root of 16 is 4. 1 minus sine squared is cosine squared. That's right. Okay. Now, just want to do one more real quick. I desperately want you to see that the form of this tells me which trig function will work, because the form of this is the same as the form of that this thing is in, is that the identity that it's in. Maybe. So cosine and sine, something minus one of them is the other one. 1 minus one of them squared is the other one squared, correct? That's why number minus function squared, that function can be sine or cosine. It would work. And the other one we did when it was, what was the other one we just did? I forgot already.
We did with secant.
It was 9 minus, no, what was it?
It was a squared minus 9.
Thank you. A squared minus 9. So when it's function squared minus number, that's like secant squared minus 1. It's the form it's in tells me what to use. Now, how does this relate to calculus? Okay, I'm going to take this away. So what if I had to do this? Yeah, let's just do this. Let's see what this does. This crazy ass thing. Now what's wrong with this? Why is this a problem that we can't even do until I show you how what we just did applies here?
You want to
Can you use use of?
That's all I'm doing.
Why? What's missing to be able to use use of?
the derivative.
Yeah, there should be a what out here?
A 2x.
An x, and the numbers I don't care about. There could be a 7x, there could be, it just has to be an x in there, right? I can make the constants do whatever I want them to. I have total control. The variable part I have no control. Does that make sense so far? So you can see what you're missing so that use of would work. So their use of can't work. Shit, right? And this is obviously not tangents and secants and shit, so it doesn't work. So what we do is we do what we just did. What do I let x equal? What we just did. 4 sine theta. And look at, so we would never think that we are allowed to do this. And I understand that. But now you're starting to see the level to which you can adjust an integral. An integral is just a form. What is x? We don't know. Could it be 4 sine theta? Of course it could be. I don't know what the shit it is. Right? Couldn't it be equal to 4 times sine of something? Of course it could be. I don't know. Maybe. No. So all we're doing is we're taking one unknown and replacing it with another unknown. But once I do that, what happens? Well, it's dx. Don't overthink it.
4 cosine theta.
4 cosine theta? Keep going. D theta. Yes. Don't overthink it. 4 goes to the right, sine's derivative cosine, right? That is kick-ass. We haven't had that happen yet. Freaking dx is just described to me. I just gotta plug that shit in. I'm not used to that. Right? We're used to du equals bullshit with dx, and I'm like, oh, I gotta make that happen. Right? So, you guys kind of follow what I'm saying? So I'm trying to point out the parts of this that are nice. If you end up hating this, you're like, at least that part's nice. You can just put dx in directly. So what happens here? 16 minus
16 sine squared.
16 sine squared. dx is 4 cosine theta. Right? I like it. I really understand that. Probably people are out there saying, why am I allowed to do this? Right? Why are we allowed to call things we don't know x? Why are we allowed to do that? Well, if I have something I don't know, why can't I just call it some other thing? Some other variable. I don't know what the shit it is. I'm going to call it this instead. And that sounds weird. I know it does. But if if you think about it, that's basically how we built a lot of our stuff. We don't know something, we give it a variable name. Well, why can't we give it a full function name? Why can't we do that? Okay, stay with me.
Variables are easier to describe than functions.
True. Now, this we already did, right? Remember, it came out to be square root of 16 is 4, 1 minus sin squared is cosine squared, square root of cosine squared is cosine. So we just got 4 cosine theta when we did this earlier. Is that cool? 4 cosine theta times 4 cosine theta, is that cool? This is 4 cosine theta?
16
Times 4 cosine theta is 16 cosine squared theta. And do you guys remember, did we just do something earlier like this?
So didn't we already do the integral? Like that's what how we got fourth sine. Oh no, that we didn't do the integral.
That was just simplifying
We just
this.
find it.
We haven't
Okay.
done the integral at all yet.
I got
Yeah. Don't get too excited. Didn't we do something like this earlier? In fact, didn't we do a 4 power here?
Yeah.
So this is gonna be easy as shit compared to that. What do I use here? Power reduction, yeah, right? So this would be 16 integral, what time is it? I did promise we'd get out early.
We got time.
Cosine squared, oh, thanks, man.
We're good.
What do you replace cosine squared with?
1 minus sine. No,
1
no.
plus 1 plus
1 plus
cosine.
cosine 2 theta.
Yeah.
Is that cool? So now I can make it an 8, is that right?
Yeah.
Yeah. 8, what's the integral of 1 d theta? Theta. And what is the integral of this is out here, what's the integral of cosine 2 theta?
1/2 sine 2 theta.
Yeah, 1/2 sine 2 theta. Plus c. All right, let me stop for a minute. We're not done. Somebody see, first off, is everybody cool with what just happened there? If you can see it? Sorry. Should be a tiered room, that'd be great, but oh well. I'll pull this up here. I don't want to mess you up. So we got 8 theta plus 1/2 sine.
Would it be 4 sine 2 theta?
Sorry?
It would be 4 sine 2 theta?
Oh yeah, because I needed to get
Okay.
the 8 in there.
Thank you.
4 sine 2 theta.
Yeah, I was scared.
We're gonna substitute theta in terms of x.
Beautiful. So
Yeah.
now, that's beautiful. So how do you know you're done with the integral? If you're using some kind of substitution, you have to come back to the original variable. Shit! Right? What do we know about the original variable? X is 4 sine theta, so sine theta is x over 4. Do I see a sine theta?
No.
I don't. I will in a minute, because what can I do with this? What's sine 2 theta? So I get 8 sine theta cosine theta. Oh, you guys are gonna love this. By the way,
Oh, it does.
so see how we defined x to be 4 sine theta, right? Which means, first thing we did was x is 4 sine theta, which means that sine theta is x over 4, correct? Which also means that theta is what? Solve for theta.
Inverse sine.
Yes, inverse sine. So I know what to put here now. Because I need, again, what variable did we start with? I better end with x. So theta is inverse sine x over 4. And what's sine theta? What's sine theta?
X over 4.
X over 4. Now, how do I figure out what cosine theta is? Oh, you guys are like, I don't know, man. Just make it stop. We're almost there, we're almost there. If sine theta is x over 4, here's my favorite way to do this. Just make a triangle, right?
Oh, 4.
If sine theta is x over 4, which side's x? That's
Yeah.
right, the y side. Which side's 4?
Hypotenuse.
Yes. And so what's cosine theta? I need this side, right? This side is? Interestingly enough,
16 minus x.
of course, right? Interesting.
Why?
So then what's cosine theta?
Because you're going backwards.
What's up? Sorry.
Wait, so theta is
It's
sine
we-
arc sine x over 4, so it'd be sine of arc sine x over
It's,
4? Or would that cancel?
Well, yes, sine of arc sine cancels, because that is an inverse function, right? Two inverse
Eight
functions
x
kill each other.
Okay, okay.
root 16 minus x squared over 4.
Is everybody cool with this here? Okay, we made this substitution correct,
Mhm.
which means this is true. So anywhere I see sine theta, I can put an x over 4. Bam. Anywhere I see cosine theta, I can use this information. This is one way to do it. You could also use sine squared plus cosine squared equals 1 and solve for cosine.
Oh,
Right?
okay.
I don't know. Is that better?
No, I
I just like this way myself. But
Let
you
me
can do it
make
that
the
way.
triangle.
It's-
Oh,
But
the
it would,
triangle.
yeah, but cosine would then be.
Here, cosine would just be that over 4, right? So then you get 8 arc sine x over 4 plus 8 divided by 4 is 2, 2 divided by 4 is 1/2, so I get x squared is 16 minus x squared over 2 plus c. Crazy shit. Crazy shit. Now, everything you do leads to the next thing. You're never like dangling. So you chose this. Why did you choose this? Because the form this was in. It's number minus function squared. That looks like 1 minus sine squared. It's cosine squared. It tells you which trig sub to do. So if it was 16 plus x squared, no. What's 1 plus function squared equals another trig? 1 plus what trig squared equals another trig? 1 plus what
Tangent
squared?
Tangent
Tangent squared. 1 plus tangent squared is secant squared. So if this was a plus, I would have used 4 tangent theta. That's the key. Now I've done a lot more with this than I intended, to be honest. So if you don't quite get this, don't worry. We're going to do much more of this next time, and then we'll do a little baby sneak peek into the next thing. Right? It just won't stop.
This one is just to make us not sleep tonight.
Sorry?
This one is just to make us not sleeping tonight.
Yes,
yeah.
yes. I'm trying to make you have calc nightmares. Really.
Can I have help on 68 for 7.1?
Say again?
Help on 68 for 7.1?
Yeah.